In this video, we're going to look at solving exponential equations using logarithms. Let's look at an example of a basic exponential equation. 2 to the power of x is equal to 8. So this is an exponential equation. The unknown is in the power. This one is nice and straightforward. 8 is a power of 2, and we could just write that x is 3. Alternatively, we could write now 2 to the power of x is equal to 2 to the power of 3. The bases are the same, therefore we equate the powers. X is equal to 3. If we had now, for example, 8 to the power of x is equal to 16, again, we can manipulate these to write these as powers of 2. So this would be 2 cubed to the power of x is equal to 2 to the power of 4. Using the rules of indices, 2 to the power of 3x is equal to 2 to the power of 4. Bases are the same, therefore 3x is equal to 4 and x is equal to 4/3. Again, you might have even spotted that. Take the cube root of 8 gives you 2, and then take 2 to the 4th power, that's 16. These are nice. We can either now simply work out the value because we got powers of 2, or we can go ahead and now manipulate it and work out the value of x. That's not always going to be the case, and we're going to need to use logs to solve for the unknown power. If I had, let's just do one, let's go for 5 to the x is equal to 17. 17 is not a power of 5. If we think now 5 to the power of 1 is 5, 5 to the power of 2 is 25. The solution to this equation is going to be somewhere between 1 and 2. Closer to 2, but we need to work that out. We've got a couple of different approaches to this. One is to go back to our definition of the exponential and logarithmic equivalent statements. We saw in the first video, if we have now a to the power of b is equal to c, this is the exponential. The logarithmic statement could now be log to the base a of c is equal to b. Remember, the log is simply now the power the base is raised by to give a certain value. So if I wanted to do this here, if 5 to the power of x is equal to 17, we can write from this now that log to the base 5 of 17 is equal to x. If you want to view it now that you're taking the logarithm to the base 5 of both sides, you could do. This, though, is just simply rewriting the exponential, the logarithmic equivalent statement from the exponential. So we can go ahead and just put this in a calculator. So log to the base 5 of 17, about 1.8, somewhere along those lines, 1.76. So x is going to be 1.76, and that's the 3 significant figures. So that's the first way. Now, another couple of ways that you could look at this. If you just say, instead of thinking I'm going to rewrite the logarithmic equivalent of the exponential, you could just say I'm going to take base 5 logarithms of both sides of that equation. That now is exactly the same as what we're doing here. We're taking base 5. I know that log to the base 5 of 5 is going to give me 1, so this is just going to give me x is equal to log to the base 5 of 17. We've already seen now that log to the base a of a is 1. Therefore, log to the base 5 of 5 to the power of x is just going to be x. And that puts us exactly where we were here. That's the first approach. If I now do the next approach, it's entirely up to you. 5 to the x is equal to 17. At this stage, I'm going to solve the equation slightly different and take logs of both sides using any base I want. As long as I'm consistent, I can use any base I want. Generally speaking, we would use base 10. So log of 5 to the power of x is equal to log of 17. Whatever I do to one side of the equation, I need to be consistent and do that on the other side. At this stage, I'm going to use the power law and bring down the x. We saw the power law in the last video, so we get x log 5 is equal to log 17. Log 5 and log 17 are just values. This is now the power 10 is raised by to get 5, and this is the power 10 is raised by to get 17. So all I need to do is divide through now by this quantity log 5, and we get log 17 divided by log 5. Don't fall into a trap here saying we can cancel the logs and it's just 17 over 5. That is not correct. If we go ahead and do that and look at this on here, what we've got now here is, I'll put it in a fraction, look nicer, log 17 over log 5, and that will give us exactly the same, approximately 1.7 odd, 1.8, whatever it was in the last bit. Just close that off for 1.76. There we go. Now I didn't need to use base 10. I could have used any base. Let's, put in log to the base 23 of 17, and then I'm going to divide this now by log to the base 23 of 5. It doesn't matter as long as you're consistent. That will give us what we wanted. I couldn't though have log to the base, let's put in here 45. That's not going to give us what we wanted. We need to be consistent with our bases. But of course, base 10 is easier. We've just got now log. So that's two different approaches. It's entirely up to you. With these ones, it's probably easier to use this particular method. In later ones, I go for this approach. So let's go ahead and look at solving some of these. Solve the following, giving your answers to three significant figures. So if 3 to the x is equal to 14, we can simply write that x is going to be log to the base 3 of 14. Now if you think about it, 3 squared is 9, 3 to the power of 3 is going to be 27, so it's going to be somewhere near 2. So let's do that. So here, log to the base 3 of 14. And that's going to give us now 2.4. 2.40, so let's write that in. 2.40, and again, that is three significant figures. So nice and logical. If you've taken logs, log now of 3 to the x is equal to log 14. X log 3, bringing the power down using the power law, is equal to log 14. And x is going to be equal to log, and I'm using, of course, base 10 over log 3. And that now gives us the same value. Right, let's have a look at the next one. Okay, with this one, what I'm going to do is simply write now that on here, x minus 1 will be equal to log to the base 5 of 9.4. This time I've got x minus 1, not x. All I need to do is add 1 to both sides. So x is going to be equal to log to the base 5 of 9.4 plus 1. And we can go ahead and evaluate that in a calculator. So if we do that, let's go for that. Log to the base 5 of 9.4, so 9.4, and it's plus 1. The plus 1 now is going to be not incorporated in this logarithm, it's just adding 1 on the outside, 2.39. So x is going to be equal to 2.39, and that again is three significant figures. Now if you think about this, if we subtracted 1 from there, what this is essentially saying is 5 to the power of 1.39. Now 5 to the power of 1 is going to give us 5. 5 to the power of 2 is 25. So that looks, well, relatively realistic. Right, so there we go. Let's look now at the next one. We've got 2 multiplied by 6 to the power of 2x plus 3 is equal to 3.4. The first thing I'm going to do at this stage is divide both sides of the equation by 2. So we've got 6 to the power of 2x plus 3 is equal to half of 3.4, which will give us 1.7. So I can write 2x plus 3 is equal to log to the base 6 of 1.7. 2x is equal to log to the base 6 of 1.7 minus the 3, and then we can say x is going to be that quantity divided by 2. So x is log to the base 6 of 1.7, we're going to minus 3 and then divide by 2. So all I've done is simply work that back. We're solving now for x, and we would work it in the same way we'd work any equation. So let's just put this in. What we're going to have then is log to the base, so log to the base 6 of 1.7, and then we're going to subtract from that 3, and then we're going to divide that by 2, and that's going to give us negative 1.35. Let's write this here, negative 1.35, again correct to three significant figures. So if we just put this back in, let's go ahead. So all I want to do is put 2 multiplied by 6 now to the power of 2 lots of my answer plus 3, and that should give us now the 3.4, which quite clearly does. So there we go. That works out nicely. That's the value that we get. Right, let's look at this one right here. I've got 2 to the power of 1 minus 3x plus 3.1 is equal to 9.7. So what we can say then is 2 to the power of 1 minus 3x is going to be equal to 9.7 minus a 3.1, which is going to give me 6.6. So 6.6. So we can say that 1 minus 3x is equal to log to the base 2 of 6.6. So I'm going to add 3x to both sides, subtract log to the base 2 of 6.6. So 1 minus log to the base 2 of 6.6 is equal to 3x. So we can say 1 minus log to the base 2 of 6.6 divided by 3 is going to give me the value of x. So let's go ahead and get that. So that's going to go in there. So we've got now 1 minus log to the base 2 of 6.6. So let's do that. And that divided by 3, and that's going to give me negative 0.574. So x is equal to negative 0.574. I think that looks good to 3 significant figures. Yeah. Okay, right. So if we did this now, what if I did 2? Let's do this. Just check that value. 2 to the power of 1 minus 3 lots of my answer plus the 3.1. That should now give us the 9.7, and we can see on there 9.7. So there we go. That's that approach. Okay, let's move on and look at some more. Now these ones have unknowns in both powers. So here what we've got now is 3 to the x minus 1 and 2 to the x plus 2. So we're solving as we were before. With these ones, we can continue the method I was using, or we could simply take base 10 of both sides. I'll do it both ways. You can decide on the first one. So what we've got then is 3 to the x minus 1 is equal to 2 to the x plus 2. Clearly, we can't manipulate these bases to be now powers of any particular value. What I'm going to write is x minus 1 is equal to log to the base 3 of now 2 to the power of x plus 2. So this is one approach. So all I've done is taken base 3 logs of both sides. Clearly if I take base 3 log of this side, we're just going to have x minus 1. Or if you like, you're rewriting the exponential statement. I'm now going to bring the power down. This power right here can be written as x plus 2 multiplied by log to the base 3 of 2. I want to get the x's on the left hand side, or if you like the right hand side, and I want to get now the numeric values on now the right hand side. So x minus 1 is equal to x multiplied by log to the base 3 of 2 plus 2 lots of log to the base 3 of 2. So x minus x log to the base 3 of 2 is going to be equal to 2 lots of log to the base 3 of 2 plus 1. So what you can see at this stage now is that I've got x's on one side, or now terms in x on one side, and then terms without an x independent of x on the right hand side. Factoring this, I'm going to have x 1 minus log to the base 3 of 2 is equal to 2 log to the base 3 of 2 plus 1. Dividing through by the content of the bracket, 2 log to the base 3 of 2 plus 1 divided by 1 minus log to the base 3 of 2. So you can see with these, when we've got the powers in now, both of our or the unknowns are in both powers, then it's slightly harder. So let's go ahead now and just evaluate this on a calculator. So in the calculator, let's just get that there. So what we've got then is 2 lots of log to the base 3 of 2 plus 1 divided now by 1 minus log to the base 3 of 2. So if we go ahead and do that, that's going to give us 6.13. So let's go ahead and do that. X is going to be equal to 6.13, and that's 3 significant figures. So if we look at that, that is what we're going to have. Now, alternatively, what you could have done is just taken base 10 of both sides. So we'd have log of 3 to the x minus 1 is equal to log, and this, remember, is base 10, of 2 to the x plus 2. At this stage, we bring the powers down on each side. So x minus 1 multiplied by log 3 is equal to x plus 2 multiplied by log 2. So this is just base 10 now of 3 and base 10 of 2. At this stage, I would expand the brackets, so you'll have x log 3 minus log 3. Remember, log 3 is just a number, is equal to x log 2 plus 2 log 2. I'm going to collect the terms in x on the left-hand side. X log 3 minus x log 2 is equal to, now, 2 log 2 plus the log 3. Factoring on the left-hand side, x will have now log 3 minus log 2, and that will be equal to 2 log 2 plus log 3. So x is going to be now 2 log 2, or if you want to say log of 4, bringing the power up, it really doesn't matter. I wouldn't if this was an equation. The more you try and simplify it, the more prone you are to errors. Log 3 minus log 2. So that's all I've done. I've just taken base 10 of both sides, brought the powers down. I've gone through it fairly quickly, but as you can see, either way. Right, let's look at that and we'll find out what that is. So that's 6.13, so we should get the same value. So 2 log 2, so again we're using base 10, 2 log 2 plus log 3, and we're going to divide that by log 3, so log 3 minus log 2, and that should give us the same value, and then we got 6.12, blah blah blah, etc, etc. So there we go, entirely up to you. Yeah, there we go. Right, let's do the next one. I'm just going to take base 10 of this side, base 10 of this side. So what we'll have then is log 5 base 10 2x minus 3, and that's going to be now log of 7 to the power of, what have we got, x plus 1. Right, x plus 1. So we can say 2x minus 3, using the power law which we saw in the last video. Log 5 is equal to, power law again, x plus 1 log 7. Log 7 is just a number. It's the power 10 is raised by now, or the power 10 is raised by to get 7. So let's multiply this out. 2x log 5 minus 3 log 5 is equal to x log 7 plus 1 lot of log 7. Okay, I'll do this in one hit. I'm going to get x over here, and I'm going to have 2 log 5 minus 1 log 7. And then I'm just going to add the 3 log 5 to both sides. So it'll be log 7 plus 3 log 5. Hopefully you'll follow that. All I've done is added so I subtracted the x log 7 to both sides and added the 3 log 5 to both sides and factored. Okay, at this stage we would have now x is equal to log 7 plus 3 log 5 over the content of the bracket, which is 2 log 5 minus log 7. If you want to show an additional step here, just go through exactly what I did on the last one in terms of collecting up the x's on the left hand side and factoring it. I've just gone there, as hopefully that's you're comfortable with that. So log 7 plus 3 log 5, and then on here 2 log 5. I could have taken any base, I really could have, as long as I'm consistent. So I can't just change these bases as we saw before. That will give me now 5.32, so x is equal to 5.32. Okay, let's see if that holds. Let's just shift store A. So if we do 5 now, so 5 to the power of 2a, or you could just put your answer at this stage, 2a minus 3, that gives us that. If I do now 7 to the power of a plus 1, that's going to give us now the same value. So we can see that that value works for that equation. Okay, what we've got here now is 7 times by 5 to the power of 2x minus 3 is equal to 7 to the power of x plus 1. What you'll notice is that this is very similar to the last question. With this one though, we've got a couple of choices. I can just go ahead and take logs. If you did that, what you'd have is log of 7 times by 5 to the 2x minus 3 is equal to the log of 7 to x, the x plus 1. So I could split this up and say that this was going to be log 7 plus now log of 5 to the 2x minus 3 is equal to log of 7 to the x plus 1. And you could have dealt with that. Remember, that is just a number. So when you have your numeric values on the right hand side, you're just going to include that. Alternatively, if you're really cheeky here, you can divide both sides of this equation by 7. So what we've got is 7 to the first. Now 7 to the first is just a constant, and that's 5 to the 2x minus 3 is equal to, and here, if you want, you can leave it exactly like so, but all this is 7 to the first times by 7 to the power of x. So we could just write this as 5 to the 2x minus 3 is equal to 7 to the x, and go from there. Again, entirely up to you. But hopefully you can see how that one would differ. So at this stage, if you wanted, you could simply write that 2x minus 3 is equal to log to the base 5 of 7 to the power of x. 2x minus 3 is equal to x log now of log to the base 5 of 7, and then just go ahead and collect those up. So x 2 minus log to the base 5 of 7 is going to be equal to 3, and then divide through by the content of that bracket. So x is going to be equal to 3 over 2 minus log to the base 5 of 7 if you wanted to go for that approach. If we did that, let's see what that looks like. So 3 over now 2 minus log to the base 5 of 7. And that's going to give us the value of 3.79. So if I just do shift store 8 and we'll store it in, let's just have a look at that. So let's see, 7 times by 5 to the power of 2 lots of that. I could put answer, I could put a minus 3. That gives us that. And then if I did now 7 to the power of, let's put that in, a plus 1. So a plus 1, that gives me that. Okay, so you can see that that is the same value. Right, last one on here. This one now, we can't divide both sides by 10. If we had 9 to some power, we could be cheeky. This stage, all I'm going to do is simply take logs of both sides, and I'm going to take base 10. So if I take base 10, what I'm going to have is log now of 10 multiplied by 7 to the power of x minus 3 is equal to log now of 9 to the power of x plus 1. Splitting this up, we're going to have log 10 plus log of 7 to the x minus 3 is equal to log of 9 to the x plus 1. That is just 1. Log to the base 10 of 10 is 1. Plus, then we're going to bring the power down, x minus 3, and then we'll have log 7, plus bringing the power down, x plus 1, multiplied by log of 9. So it's equal to, let's put that there, is equal to. Okay, right, let's expand all this out. So 1 plus x log 7 minus 3 log 7 is equal to x log 9 plus log 9. At this stage, I want to collect x's on one side and numbers on the other, so I'm going to have x log 7 minus x log 9 is going to be equal to now log 9 plus 3 log 7 plus the 1. So factoring x will have log 7 minus log 9 is going to be equal to log 9 plus 3 log 7 plus 1. So dividing through by the content of that bracket, x is going to be equal to log 9 plus 3 log 7 plus 1, all divided by the content of the bracket, which is log 7 minus log 9. Okay, so let's go ahead and look at that. That is one approach, not the only one, but it will certainly do what you want. So log 9 plus 3 log 7 plus 1, that's now on here. Let's is that going to be plus 1, or that should be minus 1, shouldn't it? Minus 1, let's put minus 1, minus 1. Yeah, that was, I don't know why did we, I think it's because I added that, right. So minus 1. This is why checking at the end is always going to be good. So log 7 minus log 9. Let's put this in. Okay, negative 22.809 and so on and so forth. So negative 22.8 to 3 significant figures. Let's put that in. So x is equal to negative 22.8, and that is to 3 significant figures. As you can see, this is prone to errors. I wasn't thinking what I was doing here, and for some reason wanted to do that. Right, so let's see if this now is good to go. So shift store A, I'll store it as my answer. So what we'll have is 10 times now 7 to the power of that value minus 3. And that is going to give me that 1. What have we got on there? 1.54 blah blah blah, and there we go. That's what we're going to have. So let's check that that is correct. That is going to give us 1.543 and so on. 10 to the negative 21. Right, let's just look at 9 to the power of that answer plus 1, and that's going to give us now, there we go. So that does hold true. So yeah, again, just be careful. I'll say that it's, as I'm talking through, I'm allowed to make silly little mistakes. Fortunately, I caught that one in time, and then we've got the correct answer. So that is using logarithms to solve exponential equations. In the next video, we will look at solving logarithmic equations by using log laws, combining and rewriting an exponential statement. But hopefully for now, that has assisted you with the basic solutions to these exponential equations.